Okay, we're going to look at this first question, which is constant acceleration in 2D and Newton's second law in 2D using vectors. Okay, so what is Newton's second law? It's the first one we're going to use here. So we're given some forces, we're given a mass, and we're trying to find the acceleration. So Newton's second law tells us that F equals ma. Now we've got two forces, we're going to add them up. So even if you see in a question it talks about resultant, it just means the result of adding the two up. So we're going to try find the acceleration. We rearrange that, we get F over m. So we've got 8i plus 9j plus minus 2i minus 7j, all divided by the mass, which is 0.6. So what I'm going to do in my calculator is I've got 8 minus 2, which is 6, divided by 0.6, which gives me 10. So I've got 10i, and then I've got 9 minus 7 divided by 0.6, which gives me plus 10 over 3j. And that's my acceleration, so it's meters per second squared. Then it says at time t equals 0, the velocity is minus 12. That's nice. At time t equals 3, p goes through the point A, and then F1 is removed, and only F2 is used. And then at t equals 8, so between here we've got 5 seconds, it goes to point B. Right, so what essentially we need to find out is where the velocity of P when it gets to A. So when it does that, it means it's its starting velocity for its journey from A to B. So first we're going to start with V equals U plus AT. Now that's one of your SUVAT formulas which you're given. So there's our SUVAT formulas in our formula book. So exactly the same way, we've got V equals, so we're starting off with minus 12j, so that's our U, plus your acceleration times by time. And we've got 3 seconds, 10i plus 10 over 3j. So let's do our i's first. Now it's quite confusing when you have just j, so if you have to write 0i for yourself, do that. Right, so we've got 3 times 10, so 30i, 3's cancel, so I'm going to have 10 minus 12, so minus 2j. Okay, so that's going to be my velocity at t equals 3, which is also going to be my opening velocity for the journey from A to B. Okay, so now what do we know? Now we need our new acceleration. So we're going to have a new acceleration. We already did A equals F over m. This time the force 1 is removed and we've only got force 2. So minus 2i minus 7j over 0.6. So we get minus 2 divided by 0.6 to give us minus 10 over 3i. And then we've got minus 7 divided by 0.6 to give us minus 35 over 3j. Okay, so that's our new acceleration, and we want to know how far it travels from A to B. Now we don't care about where it starts because we're just trying to find the distance it moves. So we're going to use S equals UT plus a half AT squared. Our old V, this V here, becomes our new U because that's the speed it's going at 3 when everything resets and we get this new acceleration. So it's going to become our U that we use, 30 minus 2. Our T is 5 because 8 minus 3 is 5. Plus a half. I'm going to write it this way around just because it's easier to sort the numbers, and because I made the question up, the numbers probably don't come out very nicely. So we end up with 30 times 5 plus 0.5 times minus 10 over 3 times 5 squared. So we end up with 325 over 3. Then we've got minus 2 times 5 plus 0.5 times minus 33 over 3. Oh, was it 33 over 3? 35 over 3, sorry. Can't read my own writing. So we've got 35 over 3 times 5 squared. Right. And we get minus 935 over 6. So we've got 325 over 3 minus 935, so that's I, minus 935 over 6 j. Now that's going to be my displacement of A to B, so like the vector going that way. If I want the distance, I've got to square and square root it. So I'm going to take 325 over 3 squared, and it doesn't matter whether it's positive or negative, because it all becomes positive. And if I stick that into my calculator, like I said, hopefully their numbers will be a bit nicer if you do any questions like this. But you never know. You know, sometimes the numbers come out horrible and we just assume we've done it wrong. And we want that to 1 decimal place. So I've got 189.8 meters. Explain why the distance travelled as it moves to A and B is not the same. Well, for A to B, when we're talking about in vector form, we assume it's moving in a straight line. So you're going to say the particle P doesn't move in a straight line. Right, so in this question, we're looking at horizontal and vertical vectors. We've got due east and due north. We've got at 11 a.m., a ship leaves the port and moves with constant velocity, right? So it's constant velocity, there's no acceleration there. And we've got to show what that velocity is, and you look at the units if you're unsure what you're talking about. So we've got kilometers, so we know that's our displacement. And it's over 36 minutes. So we're trying to show the velocity in kilometers per hour. So we want to know how many hours are on the denominator, and on the top we want to know how much it's moved. So essentially what the vectors are telling us is that this is where I started, this is where I ended. I'm going to do this, take away this to find the displacement, so how much I've moved, and then divide it by the time in hours. So if I take my V equals 4i plus 6j, and I'm going to write the alternative if you prefer working in column vectors, and that's divided by the time in hours. So we've got 36 minutes out of 60 in total. So that gives me 4 minus 2 to give me 6i, and then I've got 6 minus 9 minus 3j divided by 0.6, and that will give me 10i minus 5j kilometers per hour. I could have written it as 4/6 if I find it easier to navigate, and that's also not a problem. So you end up with 6 minus 3 over 0.6, which equals 10 minus 5. But because it's given it to you in the IJ form, it might be better just to convert your answer in the last step to that. Okay, so part B. We're looking for a position vector. So what we want is an expression which tells us no matter where the ship is, how many hours it's been, we can plug t in and find the coordinates. So you might have seen it written like this. So r0 plus vt. R0 is essentially, where did we start? We started at minus 29. And every t hours, it's moving the equivalent of 10 across and minus 5 down, right? So what we're doing is saying, say we start here, and then we're moving 10 across and minus 5 down. Now, we don't really do that. We go along the diagonal, but it's represented by doing that. Now, what I would always do at this point as well, you could have left it like that, is write your solution and put your i's together and your j's together. So that's putting in column vector form. You can also write it as minus 2 plus 10ti, 9 minus 5tj. Preference is yours, however you've learnt it and whatever you find easiest. Okay. So now we've got at 12:48 a.m. a passenger on the ship notices the lighthouse is due east. So now if we think about it, if we draw our compass, my very dodgy one, I don't know how you ever learnt it. So if we have never eat shredded wheat, but anyway, northeast, southwest. Okay, we know at 12:48, what is T? So remember, we started at 11 a.m. So we've got 1 hour and 48 minutes. So I would write at 12:48 a.m. T equals, so 48 over 60, which is going to give you 0.8. T equals 1.8, so 1 hour. So if we substitute that into here, we're going to get R equals minus 2 plus 10 times 1.8. So 18I plus 9 minus 5 times 1.8, which is going to give you 9J. So you're going to get 16I, and the J's disappear, which makes logical sense because we're expecting it to be to the east of us. So let's put, actually what I'm going to do is let's take this line here, shift it a bit so you can actually see what I'm drawing. All right, so we've got, okay. So if we're also going to consider this our IJ axes, we're going to have 16I, which is going to be here. And we know at that point there, the lighthouse is to the east of that. So it's somewhere along this way. So somewhere on that yellow line. Okay. Now we're told at 1 p.m. So at 1 p.m. So that's when T equals, sorry, this should say 12:48 p.m. Apologies. That makes more sense. At 1 p.m. So that's when T equals 2. Okay. R equals, so let's plug that in. 10 times 2 is 20, minus 2 is 18. 18I minus J. Okay, so that's going to be further along. So 18I along here, minus J is going to be minus 1J along here. So that's going to be over here, right? So that's where I am as the ship. And where you notice it's northeast, so it's along, if you like, it's in this direction. So it's going northeast from that cross. Right, I hope that makes sense. I'll draw that a bit bigger down below. So that means you can easily see where the lighthouse has to be. So if I redraw it down here, so let's say this is your 16I. We said when we're at 16I, we want it to be across here. When it's 18I and minus J, so let's say here, and it's my very, very bad scales. Let's make this longer so it's a bit more obvious. Okay. It's along here, and we know that northeast is something in this direction. So if I'm starting here, northeast for me is going to be in this direction. So northeast for me is going to be essentially this pink highlight, and I need both those things to have been correct. So therefore my lighthouse is over here. Right, now I have to work out what that is. So if I think about it, I know that it's northeast, so it's exactly 45 degrees there, which is like as if the line y equals x. So I know if this is going up 1, because we know that's minus j, so that needs to go across 1. So if that's 18, this point here must be 19. So therefore my lighthouse must be at 19I, and that is the position vector of my lighthouse. Right, next step. We've got to find the position vector of the ship when it's due south of the lighthouse. So when it's due south, what do we know for definite? So we've now got our lighthouse, which is over here. Sorry, my big L here. maybe, no, I should try not to make this look too strange if anyone's just looking at this as work solutions. Right, so that orange dot, and I know that it's due south. So due south means it's going to be going vertically downwards, right? So what do I know for definite? So it's going to be somewhere here. All I know for definite is that the I component is going to be 19. So it's going to be when the I component is 19, and that means I can find out what the T is and so on. So let's work that out. So if we do, we want to have the I component, so minus 2 plus 10t must equal 19. So 10t equals 21, so t equals 2.1, right? So when t equals 2.1, we get 9 minus 5t is going to be 9 minus 5 times 2.1 to give us minus 1.5, and that's going to be our j component. So the position vector of the ship will be, let's write it over here. So the position vector of the ship will be 19i minus 1.5j. So we know how far down it's going to be. So it's going to be somewhere here. So that's where the ship's going to be. I hope that makes sense. Okay, so we've got a walker here who's walking with constant velocity, and we want to find the speed. Now remember, speed isn't a vector, it's a scalar. So we're going to Pythagoras this. So we're doing the square root of 1.2 squared plus 0.9 squared, which gives us 1.5 meters per second. We've got a horizontal field, as shown above. At 12 noon, walker H is at a point Y. Relative to the fixed origin, we're going to write a position vector. So when we're doing this, we're saying, where is he starting? So he's starting at Y, so at 100J. Now, every single second, he is walking 1.2I minus 0.9J. And we want to, this would be your position vector. But what you're going to do is you're going to write it, all the I's together and all the J's. And we're used to having the I's first and then the J's. Okay, so it's a walker and that is this position vector. Now what that means is effectively starting here, every single second, it's as if he's going 1.2 along minus like that, but he's not really doing that. He's going along that diagonal. So that's what that represents, where he is at every second. Okay, now we've got another walker, and at noon, this walker is at K is at 9I plus 46J. And every single second, he walks 0.75I plus 1.8J. You could have written this, if it's easier for you to see, as a column, right? And then you can put your I's and J's together. 1.8J. Right. We want an expression for the distance between them. So essentially we want to go from W to K. Now you should know whenever you have that, you're doing the second one minus the first one. So it's vector K minus vector W. So I've got 9 plus 0.75T I plus 46 plus 1.8J, and I am minusing the whole of the previous bit. So 1.2 Ti plus 100 minus 0.9 Tj. So that's from over the page. Now we can only minus i's from i's. So we've got 9 minus 1.2 9 on its own, because there's nothing to minus here that doesn't have a t next to it. So we've got 9, and then we've got 0.75 minus 1.2, so minus 0.5 ti, plus 46 minus 100, which is going to give you minus 54 plus 2.7 tj. Now, show that they meet. Well, when they meet, that distance between them is going to be 0. And the way to show that is we work out what happens when the I equals 0 and check it agrees with the j equaling 0. So when they meet, wk equals 0. If I rearrange that, I'm going to get 9 equals 0.45 t. So t equals 20. If I sub t equals 20 into minus 54 plus 2.7 t, I should, if it's correct, get 0. And if that will prove that they meet. So equals 0. So they meet. Now where do they meet? They meet when t equals 20, sorry. So we're going to sub that back into either one of these original ones. So when t equals 20, so if I had 100, I had 1.2 ti plus 100 minus 0.9 t, and I'm going to sub in t as 2, so I'm going to get t is 20 even, not 2. So I'm going to end up with 24i and plus 82j. So that is my position vector of where they meet. Right, so for this question, we're going to be using F equals ma. Our F is made up of 2 forces. I'm going to be putting them in column vectors because I think it's easier to see for this question, but you don't have to. And m, it tells us, is 2, and we've got an acceleration of 1 minus 1. So this gives us 2 equations. So minus 2p, so essentially we're equating the i's and we're equating the j's. So minus 2p plus 4q equals 2. 2q minus 2p equals minus 2. I am going to rearrange the top one. So if I call that 1 and 2, I'm going to rewrite 1 as 4q minus 2p equals 2. And I am going to, well, I could either take them away from each other or solve them simultaneously, essentially. So if I get my calculator, it's much easier to do in there. I'm going to go to equation function, simultaneous equations, number of unknowns 2. That's going to be 2 minus 2 minus 2. And then I'm going to have 4 minus 2, 2. And that's going to tell me that q equals 2 and p equals 3. So now what I'm going to do is I've got my p and my q, which is the first bit. Now you could have just taken them away from each other, solved it as you normally would. And then for part B, you're going to find the size of the angle between the direction of acceleration and the vector j. So if I sketch the acceleration, we've got 1 minus 1, so we've got it here. And the angle that we want is the vector j. So remember, this is I, this is j, and it says it's positive j, so we're looking for this angle here. Okay, we know that this is 1 and 1, so we know this is 45, and then obviously we've got 90 here. So the size of the angle is going to be 90 plus 45, so 135 degrees. If you didn't remember that tan 45 is 1, you could have done tan alpha equals 1, so alpha is tan to the minus 1 of 1, which gives you the 45. Okay, so for part C. We're told, so if we take, at time t equals 0, we're given a velocity. So if we put that over here, oh, maybe not, let's try again. So we've got, at time t equals 0, we're given a velocity, and it's moving in the direction of a different vector. So let's put that here, we can see it properly. Right. So at time t equals 0, the velocity of p is 3 minus 4. So we're going to use v equals u plus at. So we know our u is 3 minus 4. We don't know what our t is, but we know our a is 1 minus 1. But we know our new v is in the direction, so it's some lambda, so it's some factor of 11 minus 13. So we're going to get 3 plus t equals 11 lambda, minus 4 minus t equals minus 13 lambda. We could add those together. That's going to give us minus 1, so 1 and 2. We do 1 plus 2. We're going to get minus 1 equals minus 2 lambda, so lambda is a half. When we substitute that back in, we're going to get our t, so we'll get 3 plus t equals 11 over 2. So t must be 2.5. And there's your final question. So a question won't tell you that it's variable acceleration. You're going to have to recognize it because you look at a t and it's to all different powers. And there's an expression where t is not constant, right? And normally when it is constant acceleration, it says it's constant. So when we've got variable acceleration, we think var, okay? And the s can have an x as well. So we've got displacement, velocity, acceleration. We differentiate down and we integrate up. So d for down and we're integrating up, okay? So we've got this x which represents the displacement. We want to know when something's at rest. When something's at rest, the velocity is 0. So to go from x to v, we differentiate. So let's differentiate this. So dx dt. Remember to differentiate, you bring the value down, you take 1 away from the power. So you're going to get 7t to the power of 5 over 2. When we take away 1. And then you can bring the next one down and you're going to get 14 times by 5 to give you 70. 70, so 14 times by 5, so you're going to get 70 over 2, so 35, t to the 3 over 2. And then you've got 56 over 3 times by 3 over 2, which is going to give you 28. And that's going to be t to the power of a half. Okay, I'm going to change that. I probably should have done that in one go and made that 35 straight away. Okay. Looking at that, it's not obvious to factorize it or put it in your calculator, but hopefully you can see you can take 7t. So you look at the numbers, 7 is the smallest number to take out. And we're going to take it out to the power of a half. So you look for the lowest power. So this is going to tell you this is going to just be t squared, because remember we add them up. And then we're going to get 5t plus 4, and we can see we've got quadratic. The question says that it wants the non-zero values, so we're not going to worry about t equaling 0. So this first bit equaling 0. We're just going to do that. You either stick it in your calculator or you can factorize it quickly, hopefully. And you get t equals 1 and t equals 4. Right. Now, when it says language of kinematics inside your advanced information, what it's trying to say is you've got to understand the difference between things like speed and velocity, distance and displacement. So now let's think what the distance, total distance traveled is going to be. So what we're going to consider is we're going to consider what happens at 0, at 1 and at 4, because that's when it's changing. Okay, so if I stick into the original one, when t equals 0, x equals 0. When t equals 1, we're going to get 2 minus 14 plus 56 over 3, which gives me 20 over 3. And when t equals 4, we get, so if I stick 4 in, I'm going to get 4 to the power of 4 to the, there you go, 2 times 4 to the power of 7 over 2 minus 14 times 4 to the power of 5 over 2. Right, put those each bits into brackets as you do it. Use your fraction buttons. They're your friends here. You know, it'll make sure you don't make any mistakes in the exam, especially if they're like really fiddly numbers. So 3 over 2, and that gives us minus 1 to a over 3. Now that doesn't mean you're going, you know, minus just means you've changed direction. You're going the other way. Right, so we start here. We move to 20 over 3. And then what we're doing, so if you imagine it on a line, you're starting over here. You're going to 20 over 3. And then you're going to minus 1 to a over 3. So the way you've travelled is you've gone up here and then you've gone back. So it's going to be double the amount of this 20 over 3. So your total distance travelled, if you want to think about it, is going to be, so I've started here, I've gone 20 over 3, then I've gone all the way there. But first I've had to go back to the 0 mark to get there. So I'm going to have 2 lots of 20 over 3 plus 128 over 3, which gives you 56. Okay, then we're told the acceleration of p when t is 4. Okay, so we've got the v to go to acceleration, we differentiate again. So we're going to differentiate again. So if we grab our differential, so when we differentiated it, sorry, our v equals all of this. So if I take that with us, so that's our v, and we've got, so v equals, we differentiate again to give us a. So when we differentiate, we've got 7 times 5 over 2, which gives me 35 over 2, and that's t to the power of 3 over 2. And then we've got 35 times 3 over 2, so 105 over 2, and that's t to the power of a half. And then we've got 28 times a half, so 14, and that's t to the power of minus a half. And we say when t equals 4, a equals, and you can just plug that in a calculator. You can also use your differentiation button. As long as you've shown you've differentiated it, you can then just put it in to get the value. Right, I hope that's useful. And all the questions are coming. They're just a little bit slow today. We've had a bit of a disastrous week. Right, this is a great question to think about projectiles in theory and how it works. So if we've got a projectile, what we're thinking about is we've got this curve. So we've got almost like a quadratic equation. And we have our initial our initial velocity, which will be at an angle. So we've got our initial velocity here. This is going to be theta. This is going to be u. And we're going to split that up. So we're going to think about it horizontally and vertically. So if you remember all that stuff that you've done, where you've got to have a look at opposite is sine, adjacent is cos. So we've got u sine theta, u cos theta. Okay, so that's all the information we're given. And we're going to think about this in terms of x and y. Sometimes much easier to think of mechanics in terms of pure maths. Okay. So we've got our Suvat equations. So our Suvat equations are exactly the same as what they are, but we're just going to think about them in horizontal world and in vertical world. So we're going to have SUVAT. We're going to split that horizontally and vertically. Horizontally, it's an x at any point. Vertically, we're thinking y. Our u is going to be u cos theta, u sine theta, and you can literally fill this out whenever you see a projectile question, unless it's in vector form, at which point you'll be given numbers for each of these. So actually vectors and projectiles is easier, right? The other thing we know is horizontally the a will always be 0. Vertically, it's minus g. The t at any given point is the same. Because a is 0, and we know that v equals u plus at, horizontally, our v is just u cos theta, and y is going to be u sine theta, and then at, which is minus gt. So now what we're going to do is find an expression for x and an expression for y. This is, the dreaded parametrics. They come up as parametrics, which we're then going to put together. So we're going to look at s equals ut plus a half at squared. So let's think of everything horizontally. We're going to have x equals u cos theta t. Now obviously a is 0, so the second half of that disappears. Vertically, we're going to get y equals u sine theta t minus a half gt squared. Okay, now if you have a look at this expression compared to the expression above, there's no t, so we want to rearrange this for t. So we take that first one and we say, well, t equals x divided by u cos theta. And we sub into 2. So we get y equals u sine theta times by x over u cos theta. So what I've done is I'm substituting. So essentially I'm taking all of this and putting it here and here, right? So that blue bit is the same as this bit. And then we're going to have minus a half times g times t squared. So x squared over u squared cos squared theta. Now, if you have a look, there's a few things that are going to cancel out. So we can see that our u's are going to cancel here. And also we'll have sine over cos, so that's going to become tan. And we've got 1 over cos squared, which is going to become sec squared. So we're going to end up with x tan theta minus gx squared on the top, so 1 times g times x squared. And then we've got 2u squared on the bottom, and all of that is multiplied by sec squared theta. Now, hopefully, if you then compare it to what's up there, everything's the same, except for over here, we've got sec squared theta, and here we've got 1 plus tan squared theta. Now, you know from your identities that sec squared theta is the same as 1 plus tan squared theta. So we can simply, from that line there, you will just essentially write the answer out. So you'll just, then your next line will just be x tan theta, I've written tan theta, they've used alpha. So there should really be an alpha there. So tan alpha minus gx squared over 2u squared, 1 plus tan squared alpha. Okay, so in an exam you could go back and change it, but I don't think they'll knock you the marks. Okay, so now we're going to use that, and we're literally just going to substitute our values in. So if I now take my diagram here, actually let's go back and grab our formula. So we're using the formula in the same form. So we want this formula, which we've just used. So if we put that over here, oops, maybe not. I will just rewrite it, it's probably easier. So we're going to have y equals x tan alpha minus gx squared over 2u squared, 1 plus tan squared alpha. Right, and this should be 10. I think it wasn't changed when we did the question. All right, so we're going to substitute in the values. We can use our y as 3.5, our x as 10, and we're trying to find alpha. So minus g, 10 squared, it tells us u is 20, 1 plus tan squared alpha. So I'm then going to times everything by 2 times 20 squared. So just so we get rid of that as a denominator, so if I do 2 times 20 squared, I get 800, times 3.5 is going to give me, so I'm doing it all in one step. If you need to do more steps, not a problem, 2,800. And then if I do that 800 times 10, I'm always going to get 8,000 tan alpha minus 10 squared g. So 10 squared is 100 times 9.8 is going to give you 980. 1 plus tan squared alpha. So if we open that up, we've got 2800, 8000 tan alpha minus 980 minus 980 tan squared alpha. And now when I should be using theta, I've used alpha everywhere. So, like I said, I don't think it'll matter too much in the exam, but you're going to do this a bit more carefully and slowly than I am. Okay, so let's rearrange that. We've got 980 tan squared theta minus 8000 tan theta, and then we've got 2800 plus 980, so plus 3780 equals 0. Oh, my voice has gone all croaky. Right, so we're going to now go to equation function. Your polynomial, don't bother simplifying it. I know you can get rid of the zeros even, but the more you mess with it, the more likely you'll make the more likely I normally make a mental arithmetic error, do something silly, and then it changes the answer. So tan theta can be 0.5035. So you've just used your polynomial, your quadratic, you're finding the solutions for tan. Now remember, tan is the one that can be above 1. And then you inverse tan both of these. So you're going to get shift tan 0.5035. Make sure you're in degrees. Let's say we'll do it to 1 decimal place. So 26.7. And if I do shift tan of the other one, you're going to get 82.6. So that tells you your theta has to be bigger than 26.7, but less than 82.6. So that's your range of values for when it's going to go over the pole. Okay, so the recording cut off before the last bit of this question, so let me talk you through it. For some reason, it didn't seem to work. So we've got our equation. We're now told theta is 60. So that means we can know our u's horizontally and vertically. We want to find the speed. Now remember, the speed is not a vector, it's a scalar, but we've got to consider both our horizontal speed and our vertical speed. In order to do so, we need to find out the time when it goes over the wall. Now we can't use the vertical bit because we want it to go over. We don't want it to hit that wall at 3.5. So we're going to use the horizontal bit of 10. So we're going to use this bit here, this horizontal bit of 10. So what we're going to do is substitute that into S equals ut plus a half at squared. Now remember, u is 20 cos 60 here. We're trying to find t, and because a is 0, all of this disappears. So we get 10 equals 20 cos 60, so t equals 1. We then find, using v equals u plus at, the horizontal speed and the vertical velocity, the components of both, which we find out here. And then we have to use Pythagoras to give us a speed, because each of those will only give us the velocity in that direction. Now, we're looking for the distance from O to C. So we want to know it's going to stop somewhere here, what that distance is. But we know the displacement vertically will be 0. So we can make y equal to 0, sub in 60. We get a quadratic in terms of x, which is our displacement. We get two values. One is going to be like almost 0. It should be 0 if it was kept all exact, because that's where it starts. And the other one is going to give you where it lands. So we get 141 meters by sticking that into our calculator. Hopefully that makes sense. And if you need any of that work through again. Okay, we've got a projectile question here where we've got two things that are colliding in this case. So we've got a football kicked from one side and something kicked from the other side, and they collide. So let's start off by resolving these initial velocity. So we've got 25 is its opposite, so sine alpha, 25 cos alpha, this way here. we've got 15 sine 2 alpha, 15 cos 2 alpha. And yeah, now we can think about SUVAT. We're going to think about P and Q. For P, I'm going to go horizontally that way, and for Q, that way. Let's do the easy ones. 0 minus G, you can do that almost instantly. Whenever they meet, the T's will be the same. We've already worked out the U's, so 25 cos alpha, 25 sine alpha, 15 cos 2 alpha, 15 sine 2 alpha. I'm going to call this XP, this YP, I'm going to call this XQ, and this YQ. Right, now what do I know? I'm told in the question the total distance here is 72. So that means at any given point, XP plus XQ equals 72. And when they meet, I know that YP equals YQ. So now what I'm going to do is use my SUVAT equations there, and I'm going to use this one here to get expressions for XP, XQ, YP, and YQ. Okay, so we have XP is the easy one because A is 0. So 25 cos alpha t. YP is going to be 25 sine alpha t, because we've got ut minus a half gt squared. XQ, so XQ is going to be 15 cos 2 alpha t, and YQ is going to be 15 sine 2 alpha t minus a half gt squared. So now we're going to take those equations and we're going to put them into these formulas. So if we take those over to the other page, we can do that. So we're now going to equate things. So we said that we know that XP plus XQ has to equal 72. So we've got 25 cos alpha t plus 15 cos 2 alpha t equals 72. We also know that when they meet, 25 sine alpha t minus a half gt squared equals 15 sine 2 alpha t minus a half gt squared. We've got two equations here, and we're going to try and use them to find what we need, which was the direction of motion at impact and the height. Okay, so the first thing I'm going to do, I'll probably take that second equation we have. This cancels. I can change this using my trig identities to 2 sine alpha cos alpha. So that's going to leave me with 25 sine alpha t, and if I move that over to that side, minus 30 sine alpha cos alpha t equals 0. I can take out sine alpha from the brackets. I can take sine alpha from the brackets, and I can divide the t out as well. And I'll get 25 minus 30 cos alpha equals 0. So I'm going to have sine alpha equals 0, which is just going to give me alpha equals 0, which I don't need. And I'm going to have 25 minus 30 cos alpha equals 0. So cos alpha equals 5 over 6. Okay. And if I needed to, I could do inverse cos of 5 over 6, but I'm not going to just yet. Right. Now I have a look here. I can now substitute in cos alpha, cos 2 alpha, and I can find a value for t when they meet. Because remember, I'm trying to find the height when they meet. If I find a value for t when they meet, I can substitute that into either YP or YQ, and I should get the same answer. Okay, so my alpha is cos to the minus 1 of 5 over 6, which is how I'm going to type into my calculator for the 2 alpha bit. I can calculate that if I want, actually. So if you did calculate it, inverse cos of 5/6 gives you 33.5573 and so on. But I've left it exact in my calculator. So then I've got 25 times by 5/6, because that's cos alpha t, plus 15, and then if I multiply my alpha by 2 to cos of my answer, I get 7 over 18 for cos 2 alpha t equals 72. When I rearrange that, I end up with 25 times by 5 over 6 plus 15 times by 7 over 18, which gives me 80 over 3t equals 72. So t equals 72 times 3 divided by 80, and I get t equals 2.7. So 2.7 is where they meet, is the time when they meet. So time when meet. Okay, so what we want to do is find out the height at that point. So the height at C, we can take either of them. So I'm going to take my y for, it doesn't really matter, does it? Let's take yp. So we've got 25 sine alpha t minus a half gt squared, so a half 9.8 t squared. And we substitute in what we know. So we worked out alpha was 33.3, t is 2.7, and when I work that out, I get 1.59 meters. So we've answered the height of C above the ground. Now we want the direction of motion at that point. So in order to think about that, we've got to think about the velocity horizontally and the velocity vertically, and then we can calculate both. So, and we're doing it for particle P. So we're using, right, so we have to use V equals U plus AT. Now remember, V and U horizontally never change. So my V horizontally is just going to be 25 cos alpha. My V vertically, however, is going to be 25 sine alpha minus AT. So my X, I want to find my T when they meet, and yeah, minus GT. Perfect. So G, and we know the T when they meet, which was 2.7. Right, so now we can stick that all into our calculator. So we get so we're going to do 1 divided by the other for the direction. So if I do this one, inverse, so we have as our inverse cos, sorry, 5/6. Oh wait, cos alpha is 5/6 already, sorry. 5 divided by 6 times 25. So 125 over 6. And then, and we want to sine that, times it by 25, minus 9.8 times 2.7. And that gives me minus 12.64. So my horizontal is 125 over 6. My vertical is actually going down. So 12.64. And I'm looking for that. Okay. So the angle I'm looking for is this angle here. So I want my direction of motion. Well, I could have looked for another one and then I have to compare it to the vertical. So I've got my opposite and I've got my adjacent. So tan, let's call that theta, is going to be 12.64 over 125 over 6. So that tells me that theta equals, sorry, this has got a bit long, in shift tan of 12.64 over 125 over 6, which gives me 31.2. So when I'm writing my answer, I'm describing that as below the horizontal. So the direction of motion is going to be 31.2 degrees below the horizontal. And one improvement, air resistance is always being a good one if they don't. Air resistance to be taken into account. Occasionally they say, what is there an improvement excluding air resistance? You could say you could take into account the size or the shape of the balls, you know, something like that. Okay, so as a recap, if we've got two things, we're going to think of SUVAT for both of them, think about when they meet, what happens, and then work through the algebra. This bit is just long, try work through it slowly. I know I've rushed through it, it's to try fit this video in. So, hope it makes sense. Right, so we're going to look at this question where we're resolving forces primarily. So we've got a box of 30 kilograms is at rest on a rough horizontal floor. So we've got 30G going down. Wherever we've got something going down, we're also going to have a resultant force going up. It gives us the coefficient of friction. And it tells us there are two forces, both acting in the same plane, applied on the parcel. So let's resolve those forces. So this is going to be T sine 12, T cos 12. And the reason is to go from this bottom of the arrow to the top of the arrow, you've got to go along and up. Now remember, wherever your angle is, opposite is always sine, adjacent next to is always cos. So in the same way, we go across and up. This is going to be 180 sine 20 and 180 cos 20. And then we've also got to put friction in. So I'm going to put friction going this way, because from the diagram, I can see that that's like a smaller arrow, but also if it's the wrong way, the question won't make sense and you'll get negative answers and you'll know you'll have to flip it. Okay, so it's an equilibrium. So essentially up equals down. So up equals down and left equals right. So let's do that. So we've got T sine 12 going up. We've got R going up. We've got 180 sine 20 going up, 2, 3 going up, and we've got 30G going down. And what you might want to do is once you've dealt with something, almost sort of tick them off so you know you're not going to miss any of your forces you need to be thinking about. And then we've also got left equals right. So we're going to have T cos 12 plus 0.16 R. So I've written friction straight away as mu R. So remember, friction is mu R, mu being your coefficient of friction. And that equals 180 cos 20. Okay, so we've got two equations, two unknowns. We can first rearrange the first one, and I would probably just make, so if I call that 1 and call that 2, because you've all got calculators where you can put things in using your simultaneous equations button. So minus 180 sine 20. So then I've got T cos 12 plus 0.16 R equals 180 cos 20. So there are no marks generally for sorting this out beyond plugging it into your calculator. And so let's do that. So if you've got the class whiz, you're going to menu, you're going to A, and you're choosing simultaneous equations. Number of unknowns would be 2. You could choose the X to be the T. So you literally would type sine 12, hit the equals button, it moves you along 1. Your R would be the Y, so that's 1. And in the last bit, you're just going to do 30 times 9.8. You can even use brackets in here. Minus 180 times sine 20. And hit equals again. Then the same thing, cos 12, 0.16, and 180 cos 20. And then if you hit equals, it gives you your x value, which is your t value. And if you hit equals again, it would give you your r value. Now we want the x value, so your smallest value of t is 139.652 ... So we're just going to say 140 newtons. And that would be your smallest value of t for which it remains equated to each other. I hope that makes sense. Right, so we've got another question here on equilibrium and then sliding up and down the plane. So we've got a particle of mass m, so we're going to have mg acting downwards, and then we're going to have r that way. That mg we can resolve. So if that's alpha, so we'll have mg sine alpha, because this is opposite, and mg cos alpha. Also, you're always going to get sine down the slope. So down slope is sine. We're told tan alpha is 5/12. So if I draw my triangle, that's my opposite and my adjacent. So sine alpha will be 5/13 and cos alpha will be 12/13. Then if we read through the question, we've got when x equals 4p, the particle is on the point of sliding up. So that means the friction at that point is acting downwards. Whereas in this case, the friction is acting upwards because it's on the point of sliding down. And now we want to find mu. Step 1, we're going to first resolve in order to find our r. So we know this way equals this way, so r will equal mg cos alpha. And for the moment, I'm just going to leave everything in cos and sine. And I know we know what they are, but we're just going to leave it like this for the moment. Then we know that we're going to do f equals ma, and a is 0, so then up equals down, but we're going to look at the two different, so up the slope equals down the slope, and we're going to think of the two different scenarios. So scenario 1, when x equals 4p, we're going to get what? So going upwards on the slope, remember it's the pink friction here, we're going to have x going up the slope, which is 4p, and that's going to equal going down the slope, mg sine alpha plus mu r. But instead of r, I'm going to put in mg cos alpha. And then going the other way, so this time exactly the same, we're going up the slope. Instead of 4p, we've got 2p, but we've also got mu r. It's going the other way this time, and that equals mg sine alpha. Okay, so if we have a look at that, we can now see what we can substitute. We can multiply, or we could just multiply this one by 2. So when we do that, we get 4p, and I'm going to move this onto that side, mg sine alpha minus mu mg cos alpha. These have both been multiplied by 2. And multiply the whole expression by 2. And now what I can do is I can take these away from each other. So I'm going to do 1, take away 2. 4p minus 4p, which is going to give you 0. 2mg sine alpha minus mg sine alpha is just going to give me mg sine alpha. Minus 2 minus 1 more is going to give me minus 3 mu mg cos alpha. I can cancel the mg's out, and I end up with sine alpha equals 3 mu cos alpha. Right, so we've got sine alpha equals 3 mu cos alpha. Divide by cos alpha on both sides. Sine over cos is tan. Mu equals 1/3 tan alpha. Now I know tan was 5/12, so I get 1/3 times 5/12, which is 5/36, and that is my mu. So this is another question that looks a little scary, but actually when you break it down and if you resolve all your forces properly, it's not difficult. So we've got a particle of mass km. So that P has got kmg going down. It's on a rough plane. The plane is inclined to the horizontal. We've got a force. We've got a coefficient of friction between P and the inclined plane is mu. When x equals mg, so we're saying x, this is actually mg, the particle P is in equilibrium and on the point of sliding down. Now the useful bit about this information, it tells you therefore friction acts up. So if it's on the point of sliding down, you're going to have friction, which remember we're just always going to write as mu r, sliding down. We've got our kmg, so we can write in our r like this. And then we can resolve the forces that we have. So if we resolve, so if we take the x, we can resolve it that way and that way. We've got an alternate angle there, so if that's theta, that's also theta. So we're going to have mg sine theta, because x is mg, and mg cos theta. We're going to resolve this force. This is theta. Going down the slope is always sine theta, and this is going to be kmg cos theta. And now all we're going to do, we see the word equilibrium. We've got this way equals this way. Let's do that first. So going sort of up the plane, we've got r, and that equals kmg cos theta plus mg sine theta. And what you might want to do is like put a little tick once you've dealt with some forces, just so you make sure you don't miss any. Okay, and then you can see what's left as well. So if we're going that way and that equals that way, we have going down the slope. So remember that this is going this way and this way because we're going from the top of the arrow to the bottom, so down and across. So we've got kmg sine theta, and the only other force we've not used is mg cos theta and mu r. Right, we're trying to get an expression for mu. So what we're going to do is we're going to substitute in our r. So into the second equation. So 1, 2, so we're going to put 1 into 2. So we've got kmg sine theta equals mg cos theta plus mu, lots of kmg, because we're multiplying the whole thing by it, plus mu mg sine theta. Right, now inside everything, we've got mg. So I am going to get rid of mg, 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 mg. Everything with a mu is going to go on the same side of the equation. Oh, actually, before we do that, we can see in the question we've got tan. So when we see that, we try to get there. So we know sine divided, so we know that tan theta equals sine theta over cos theta. So what I'm going to do is divide everything by cos theta. So k sine theta, sine over cos is tan, so I'm going to get k tan theta. Cos theta divided by cos theta is just going to give me 1. I've got mu k cos theta, so again, the cos theta is going to disappear. And here I'm going to get mu tan theta, because I've got sine over cos. Now I can put all my things that are not mu, well, we'll put the mu on this side, k plus tan theta. So I've just essentially rearranged it to put that side. So then this can go there. So I get k tan theta minus 1. And hopefully you can see when you divide through by that, you end up with the solution. Sorry, it's gone right into the bottom, but that's what we get there. So for part B, we want to deduce that when k equals 1, theta must be greater than 45. Okay, so let k equal 1. So let k equal 1. Then you're going to have tan theta minus 1 over 1 plus tan theta. Now we've got mu, which is our coefficient, which is our coefficient of friction. Now you can never get a negative coefficient. So we know all of that has to be greater than 0. So therefore tan theta has to be greater than 1. So then theta is greater than 45. So that second bit's quite straightforward. Even the first bit, if you got the resolving right, the rest follow. Okay, so here we've got a cylindrical drum and we've got a ramp with rested equilibrium. But the minute we see the words uniform rod, our brain is going, okay, it's a moment's question. It looks strange, but it's a moment's question. And we can take it from there. So first of all, we've got the weight W. We know it's uniform, so it's acting in the center. So we've got W there. It's on a rough horizontal ground. We've got our reaction force. We're going to have our friction over here. So we've got friction here. We've got any other forces. We've got it sitting here and it's a circle. So the normal is going to be like that. And I think for the moment, that is all we have. Now remember with moments, we're going to have up equals down, left equals right, and we take moments at A. But in this case, it's a little bit different because it's given us a question first. It says, explain why the reaction from the drum at the point C acts in a direction which is perpendicular to the ramp and calculate the length from A. Okay, so we know that ACD equals 90 degrees because AB is a tangent to the circle. And by Pythagoras, because we know the other two sides, so either you recognize it as a 5, 12, 13 triangle, or you can say the square root of 5 squared plus 12 squared is going to give you 13 meters. And now we're going to go through the process of resolving what we have there. Right, so we've got our diagram. Let me quickly put our forces back on. We had R, we had friction, we had weight, we had the normal, and that's the only thing that's not going up and down. So we want to resolve this like this. That is theta, that is also theta. So we're going to have n sine theta, n cos theta. And now we're going to go through our process. Up equals down, left equals right, and moments at A. So whenever you see a moments question, that's the process that you're going to go through. Okay, so up equals down, going upwards, I have R, and I have n cos theta, and that equals W going downwards. I've got n sine theta equals friction. I'm going to take moments at A, so I'm starting at A. Remember, a moment is the force times the perpendicular distance, so this distance here. So we've got W, this is this side of it, so this is going to be cos. So we've got W times 8 because it was uniform and the whole thing is 16. 8 cos theta equals, we get to our next force, which is N, which is already perpendicular, so we just take 12 to be the distance. So 12N. And we know that cos theta, because remember we worked this out, is 13, cos theta is going to be adjacent, so this one here, over hypotenuse. So W times 8 times 12 over 13 equals 12N. And we can rearrange that and we've got N equals, so essentially that goes 8 over 13W. So we've effectively answered part B. Right, so then in part C, we want to find an expression for the resultant force at A. So essentially that means I want the force R and FR, and then I want to resolve it because the resultant is the result of the two forces. Okay, so what we're going to do is take all this information we have and substitute things in. So we want an expression for R. So R is going to equal W minus N cos theta, but we know N is 8 over 13 W, and we know that cos theta is 12 over 13. So we got 1W minus 8 over 13 times 12 over 13, which gives us 73W over 169. And then we want an expression for friction, which is N, which is 8 over 13W, times sine theta, which is 5 over 13, and that's because sine opposite over hypotenuse. And that gives us 40W over 169. So we've now got our two values. So we've got, let's go to the next page. So we've got friction, which is acting in that direction, which is 40W and 169, and over 169. Actually, let's draw that further down so you can see properly. So we've got friction acting in that direction, and we've got our R acting in that direction. Now, nothing ever does this, right? So we can sort of shift, if you like, this line over here kind of can get shifted along here, although it's taken everything with it. So when I'm considering how to think of the resultant, I'm thinking across, I could think across and up, for example. So we've got 40W over 169, and we've got 73W over 169, and we want to find the result. So we want this one here. So we can do that using Pythagoras, and that's going to be our force at A. So we're going to do the square root of 40 over 169, and that's going to be W squared, and that's going to be square that, and 73 over 169 W squared. When I stick that into my calculator, I get root 41 over 13 W. And then it asks me for the angle. So it wants me to calculate this angle here. So theta is going to be 73W. So tan theta is going to be opposite over adjacent. So 73W over 169 it turns into a times, but let's write it out first, divided by 40W over 169. Now a divide becomes a times, and you flip the fraction. So that's going to cancel, that's going to cancel. So we get tan theta equals 73 over 40. We're going to do inverse tan, and theta equals 61 degrees. Okay, so here's another moments question with another non-uniform rod. So trying to find things that are a little bit different. So we've got a non-uniform rod of mass 5 kilograms. So we know we're going to have 5G going down somewhere, but it's not in the middle. And rests with one end A on a rough horizontal ground. So straight away we see that. We've got our R, and we're going to have some friction. The centre of mass of the rod is d meters, so we know that this is going to be d meters away. The rod is held in limiting equilibrium by angle theta. The line of action of P, so that's a force, is the same. Okay, fine. So now we just need to resolve some forces, because remember I'm going to do up, down, moments at A. So the only thing I don't have an up, down for is this one over here. So I want to figure out what this is. Now, we can see if that's theta, then using your sort of, either your angle rules, you know that that's going to be the same as this one over here, right? If you need to see why, I can show you. So if we imagine you had your Z angle, right, or your alternate angles, this bit here would also be theta. This bit is 90, so this bit here would be 90 minus that theta. And then you've got, if you like, another 90 here. So then that bit there and that bit together make 90, so it's the same theta, if you could only think of it in that way. But hopefully you can see that's the case. So this is opposite, so we get P sine theta, and we've got P cos theta. So now we've got everything we need. And we do the exact same process like we do for ladders. We're going to have up equals down, left equals right, and then moments at A. So up equals down is going to be R plus P cos theta equals 5G. Left equals right. We're going to have friction equals P sine theta. And then we're going to take moments at A. So if we start at A, the first force we come to is 5G. 5G is this much away. And remember, this is the adjacent. So it's going to be cos. So we're going to have 5G times d cos theta equals, because obviously if I'm holding it, if my point is here, that 5G is going to push the rod down, whereas the P is going to push the rod that way. So one is going clockwise and the other is anti-clockwise. So P is already at right angles here, so it'll be P4 or 4P. So that's taking moments at A. And that's without me even reading through the question. What is it asking for? It's asking for the magnitude of the vertical component of the force on the ground. So essentially it's asking me to get an expression for R and for FR. Okay. And in terms of D, G, and theta. So we're going to have lots of things in that. Right. So if I'm going to rearrange this equation here to make R the subject of the formula. And then I can figure out what I'm going to substitute in. So R equals 5G minus P cos theta. Now the thing I want to get rid of is the P, but I don't want to introduce a friction. So I'm going to use this formula to replace P with, to substitute in for P. So if I rearrange this, P equals 5G d cos theta over 4. So if I substitute that in, I've got R equals 5G minus 5G d cos theta over 4 multiplied by cos theta. So that's going to become cos squared. It looks really ugly, but that's what they want. I've got something in terms of d, g, and theta. My friction is the same as P sine theta. So 5GD cos theta sine theta over 4. And those are my two expressions. They're not very pretty, but those are the answers. Now we're told that tan theta is 5/12. So if we take this over onto the other page, and that and we've got a coefficient of friction here. So let's copy that over. And let's see what that's going to come out to be. So we've got, given that tan theta equals 5/12. So now draw your triangle out if you need to. So tan is 5/12, so it's a 5, 12, 13 triangle. We might need it. And we're told that the coefficient is a half. So we know FR equals a half R. Okay. We have expressions for everything now. So we already have an expression for FR. This is what we did before. So we have FGD cos theta sine theta divided by 4. We have R, which we worked out to be 5G minus 5GD cos squared theta over 4. And now we want to rearrange this for D, but let's see what we can cancel out. I'm going to multiply both sides by 4. So that's going to give me 5GD cos theta sine theta equals, that's going to become 2. So that's going to give me 10G minus 5GD cos squared theta over 2. And now I can see what's inside everything and cancel out to make the calculation easy to then be able to use the tan theta. So what do we have on in everything? We've got a G in everything. We can get rid of that. And I think that is all for the moment. That's obvious. I could divide through by, no, I could just replace things. It's probably easier. So if I replace everywhere that I have, so remember tan theta is 5. So everywhere there's a cos theta, I can replace it with 12 over 13 and sine theta with 5 over 13. So I get 5D times 12 over 13 times 5 over 13 equals 10 minus 5. Actually, we can put that all as one fraction, so make that 20. Time 5D times 12 over 13 squared. So I want all the D's on one side. If I clean that up, I'm going to end up, I can stick it all into my calculator, she says, without a calculator in front of her. Sorry, as you can tell, I'm working these out with you. I have the final answers, but not the work solutions, which always makes it easier to explain so you don't assume anything. So you got 300 over 169 equals 12 over 13 squared times 5 divided by 2. So I know I separated it out, but I should not have. So 360 over 169 D, and that's got a D there. Put all the D's on one side. So if I add 360 to, I'm going to get 660 over 169D equals 10. So D equals 10 divided by so I'm going to multiply by 169 over 660, and I get 169 over 66, which is the solution. Okay, so that was a bit of a messing around with algebra. That algebra bit would probably only be worth 1 mark though, so you know, your marks are for getting essentially to that point. Hope that's useful. Okay, so we've got a ladder here. Now with ladders, it's always the same. There's 3 steps you always do. You've got to resolve up and down, left and right, and you can take moments at A. But let's go through, and as long as you have labelled it correctly, these should never ever be difficult. These are like some of the most marks, but the easiest questions. Okay, so we've got a non-uniform rod. The mass is M, the length is 2L. It rests in equilibrium, but the important bit here was it's non-uniform. So what that means is we're going to put mg in, but mg is not going to be in the middle. We don't know what this length is. So we're just going to call this length x, and the whole thing was 2L. So this is going to be 2L minus x. Okay. And we know it's on a rough horizontal floor. So at A, we're going to label R. And because it's rough, we're going to have our friction always going this way. And so that's friction, and that equals mu R, and we're told the mu is 1/4. And if you always write in the mu R, you're not going to confuse your friction with force in general. And then we go to the top, and at the wall, we've got another reaction. I'm going to call that N. And I've got friction as well. So this is the friction at the, wall, which is going to be 2/3 N. I use different letters. You might use RA and RB, but that way I just don't confuse myself. Easily confused, clearly. Right, So now we've got our labeling right. This shouldn't be difficult. We're going to just follow the process. Up equals down, left equals right. Okay, so let's start with up equals down. So going up, I've got this force, I've got this force, and going down, I've got this one. So I've got R plus 2/3 N equals mg. Okay, left equals right. I've got left and I've got right. N equals 1/4 R. Right, so I'm going to call that 1 and I'm going to call that 2. And what I'm going to do is I'm going to sub 2 into 1. So I'm going to get R plus 2/3 multiplied by 1/4 R equals mg. Okay, so altogether I've got, cancel that down, 1/6 plus 1, so I've got 7/6 R equals mg. And then I can simply rearrange that to give me R equals mg, 6/7 mg. So R equals 6/7 mg. And that's going to be the vertical component at the floor. So we're done there. Now we want to find the distance AO. So they've called this point O. I've labelled that distance X, and like we said, we're just going to follow those steps. So the next bit is simply to take moments at A. So we're going to take moments at A. Now, remember, a moment is force times the perpendicular distance. So that's what a moment equals. Right, so we're going to start at A. These forces disappear. We don't care about these. We're going to go up, and with first force we come across is mg. And your perpendicular distance is this bit here. So the distance we're thinking about is this here, because what we say is from A, if we've got this point A and we've got this force going down, from this force going down, I want to go at right angles and meet A. So it's going to be that distance there. Now, that distance there is, this one's opposite, this one that we want is adjacent. Adjacent is always cos. So we've got mg times x cos 60. And then we go further up. And our next force we come across is we've got n and we've got 2/3 n. And if we think about it, if we fix this point, so if we have a point fixed over here, and the mg is going to make it go this way because we're pushing it down. The n and the fr are both going to make it go the opposite way. So they're on the other side of my equation. So that equals n times, and we want our perpendicular distance. So we're going from here, we want to go at right angles until we're sort of in line with A. So the distance that we're looking at here is this distance here, which is opposite. So we've got n times 2L sine 60. So let's just give you, that's equivalent to that blue bit, and that's equivalent to the yellow bit. And then we've got plus 2/3 n times by 2L cos 60, because the distance that we're looking at is then going to be all the way across. So we're taking our force here and we want to get to A or in line with A. So essentially the right angle to it is this length here. So all along the bottom. Right. So that's your 2L cos 60. Now what we can do is we can calculate that. So when we substitute it all in, and our distance is going to be in terms of L, we're not going to get a pretty answer. So you don't always get nice answers. The algebra and some of the mechanics questions can be a bit horrible. So we get 1/2 mgx equals, sine 60 is √3. We know from what we did previously, n is the same as 1/4 r. So if n equals 1/4 r, that must be 1/4 of 6/7 mg, right? So that's going to give us, if we cancel that down, we get 3/14 mg. Okay, so mg, a half mg equals n, which is our 3/14 mg, times 2L times sine 60, which is √3, plus 2/3 n, and n is again 3/14 mg, times 2L times cos 60. Yeah, so we've got our cos 60, which is a half. Right, now if you notice there's mg's in everything, we can cancel them all out. And is there anything else that's in everything? Nope. We don't even have a half. Okay, perfect. So now if I've then simplified that, that's going to give me a half x, which equals then 3√3/14L plus 1/7 L, just putting that in my calculator. We'll multiply everything by 2 to get x on its own, and I'm going to take L outside the bracket in the same instant. And I get 3√3/7 plus 2/7 L. And that is your exact distance. Now, they didn't necessarily ask for an exact distance, but it's going to be in terms of L. If I leave it exact, I'm going to be okay. If they had said exact and you didn't, you'd have lost 1 mark. So that's your ladders question. Up equals down, left equals right. Take moments from A. Always the case, no matter what ladder you do. There's a few more ladders on YouTube. Have a look at those, and we'll look at some other rod questions as well, because it could be any of those.